Okay, to recap where we were last time, we derived equation 3 here. Can everyone see that? Yeah?
Yeah.
Okay. We derived equation 3 systematically from our theory of finite deformation elastic plastic materials under the assumption of isotropy, the constitutive functions which depend on elastic strain or equivalently on the stress S. We assumed isotropy for those. And then we invoked the idealization of a rigid plastic material. That means we assume that the elastic strain is so small compared to the overall strain that we can safely neglect it as a useful idealization, which means the elastic deformation H is a rotation field. And that led us systematically to equation 3. And then I remarked how what a pleasant surprise this is, because equation 3 is the first equation basically in plasticity theory, the first, although we're using modern notation here. That equation was set down, I think, in the two-dimensional context, first by Steigmann and then by Levy in 1870, if you can imagine. That's before the advent of modern continuum mechanics and the very elegant formalism that goes along with it. And so in retrospect, I mean, it seems these originators of the subject had a remarkable physical insight. And so it's satisfying, I think, to be able to derive the classical model in the framework of the modern theory, especially, because it helps us to put the classical model on a firm theoretical foundation, systematic foundation. And now having that foundation, that general overarching framework of the modern theory, it affords us a framework in which we can generalize the model as needed to accommodate, say, anisotropy or other physical effects that we'll discuss a bit later in the course. So it's kind of, it's not a major thing from the point of view of the modern theory to arrive at this result. But considering that equation 3 predates the modern theory by a good 100 years or so, it's kind of interesting and satisfying that we come back to the classical theory in a systematic way. All the more so because the originators of the subject did not have a well-developed theory of material symmetry, which we invoked repeatedly in the course of deriving this result. Okay, so in fact, so if you look at the structure of equation 3, it looks more like fluid mechanics than solid mechanics in a way, right? Let me elaborate a little bit more. So equation 3 applies when the yield condition is satisfied. That's in this case, the norm of the deviatoric Cauchy stress, which we call tau. Remember, that's related to deviatoric S by rotations, because the elastic part of the deformation is a rotation under these assumptions. And the norm is unaffected by the rotation. So the yield condition can be expressed in terms of the deviatoric Cauchy stress, tau. Okay. And that equation 3, that sort of flow rule, applies when the yield condition is satisfied. Norm tau equals square root 2 times K. K we interpret it as the yield stress in shear. And if tau falls below this value, then there's no flow in the sense that D then would be 0. And then you have a rigid motion. If you've taken some continuum mechanics, or if you've seen the book by Chadwick, let's say, then you know that the necessary and sufficient condition for a motion to be rigid is for d, the symmetric part of the velocity gradient, to be 0 everywhere in the body. And that is the case if the norm of tau falls below square root of 2 times k, according to the theory. So that's the reason we call this a rigid plastic model. You have rigid deformation unless tau reaches this threshold, in which case you can have also plastic deformation. Okay, so if you look at the flow rule that says d is lambda tau, take the inner product of that equation with itself, you get lambda squared tau inner product tau. Tau inner product tau is the square of this, which is 2k squared. Solve this equation for lambda. Remember, we require lambda to be non-negative, right, in the flow rule. And we get, whoops, excuse me, hold on. Let's see if I can get back. Yeah, there it is. Solve for lambda, take the positive root, non-negative root, and you get this. And so the flow rule tells you this, or you can solve for tau and you get this expression here. So this is the stress given explicitly as a function of the deformation, or the rate of deformation tensor. And that only applies when the norm of tau equals root 2k. If that doesn't, if norm tau is less than that, then this equation does not apply. So this is a constitutive equation for the deviatoric part of the Cauchy stress. And it looks more like fluid dynamics than solid mechanics. Right? First of all, it involves only variables, the spatial variables, or Eulerian variables, if you like. Okay, so we derive this as a special case of a model for isotropic materials. In the old days, as I mentioned before, people didn't have a well-developed notion of material symmetry, although they had, of course, an idea of what isotropy was. But this is kind of deceiving. This constitutive function is what we call an isotropic function. An isotropic function, in quotes, is, say, a tensor-valued function, let's say, of d, for which that function evaluated at q d q transpose is q f at d q transpose for all orthogonal q. That's the meaning of an isotropic function. And for example, the stress in a viscous fluid will satisfy this condition, the constitutive function for the stress. We can show that this function tau hat of d is isotropic in this sense. Replace d by q dq transpose everywhere that it occurs. Downstairs here, the norm of q dq transpose is the same as the norm of d, just use the trace definition of the norm. Well, that's the square root of the tensor dotted with itself. And then the q's can be factored out, q in front, q transpose in back, so we just get q tau hat q transpose. So this tau is an isotropic function, but this really pertains to the notion of frame invariance, or invariance under superposed rigid motions. But frame invariance, on the other hand, has nothing to do with material symmetry whatsoever. So the classical theory caused people a considerable amount of confusion in the course of the development of modern continuum mechanics, because the classical theory of plasticity that we've just outlined, because while the constitutive function satisfies frame invariance, there's nowhere in that function, is there any room for a notion of material symmetry. We're able to come at it from the modern theory, but going back, I mean, there's no reference configuration or intermediate configuration relative to which we can make a statement about material symmetry in this formula, right? All variables here are defined in the current configuration exclusively. So nevertheless, people would tend to confuse the notion of isotropy pertaining to this particular constitutive function with the notion of frame invariance, which has nothing to do with isotropy or material symmetry in general. And I think for that reason, this is the main reason why the classical theory of plasticity was left out of the discussion of modern continuum mechanics since the middle of the last century. And only recently have we come full circle and been able to interpret the classical theory as a genuine, as a constitutive equation genuinely related to isotropic material symmetry. Okay, in fact, it has the structure of a viscous fluid constitutive equation, let's say with a viscosity eta, shear viscosity, that looks like √2 times k, the constant, divided by the norm of d. So this is a kind of a viscosity that depends on what's happening to the material, the rate of deformation in the material. So it's a variable kind of viscosity. The difference between this constitutive function and a conventional, say, rheological fluid, that is to say, a fluid with a viscosity that depends on the rate of deformation, this being an example, the difference between this material and such a, we would say, non-Newtonian fluid is that the constitutive equation only applies when the stress reaches a threshold value, the yield value, unlike a conventional non-Newtonian fluid where there's no such threshold requirement. Okay, let me move on to the next set of notes. Let's see, yeah. And let's enter a stage in the course here where we look into a number of examples and use the theory that we've developed, the classical theory, basically, to solve a number of examples explicitly, to get a feel for how plasticity works. In fact, since we just mentioned viscosity, this may be a good place to introduce the notion of viscoplasticity. And this notion essentially dates back nearly 100 years, 1922, to somebody named Bingham. And Bingham introduced the idea of combining plasticity with traditional viscosity. So plasticity is just the second term here. The deviatoric Cauchy stress is √2 k over norm d times d, constitutive equation we just studied. But notice we could put viscosity, conventional viscosity, we could add it to the material properties simply by adding another viscous term, a viscosity term, a conventional viscosity, to eta. Eta is the shear viscosity, say in a conventional viscous fluid. Just add that to this term and we get a combined effect of plasticity with viscosity, and that's called viscoplasticity. And this is a particular model then of viscoplasticity. And it turns out to be an especially good model of materials like paint that normally don't flow unless you reach a threshold value of shear stress, and then you can cause the paint to flow, which is how it is that paint can be spreaded on a wall. You're basically scraping the paint on the wall, that is, you're shearing it, and if you don't do that, the paint will simply stick to the wall like a rigid body. To cause it to flow, you have to produce a sufficient amount of shear stress in that fluid. So this is used quite often as a model for the flow of paint, for example. But it also is a good model to accommodate viscous effects in a conventional plastic material. Let's take a look at, so let's propose this so-called Bingham material, and have a look at some of its properties. If we take the norm of this tau, we just get 2 eta, we just get the parenthesis times the norm of d. which of course is 2 eta norm d plus root 2k, where k is the yield stress in shear. And so this model then stipulates that in order to have a non-zero deformation rate, a non-rigid motion, in other words, d not zero, if d is not zero, this norm is positive here. And then the norm of tau has to be greater than or equal to root 2k in order to get flow, a non-rigid deformation. So this viscoplastic model has the interesting feature that it's operative, that is to say, the straining of the material is non-zero, only when the stress actually lies outside the yield surface. Remember, the yield surface was defined by norm tau equal root 2k for isotropy. So this is an odd sort of thing where you have flow only if the stress exceeds the yield limit. Unlike in the case of an inviscid plastic material where there was no viscosity, you were never allowed to exceed the yield stress. Remember, the stress state outside the elastic range, so-called, was inaccessible. Now you have to be outside that elastic range in order to have a non-rigid deformation. And so because of this property, such models like this, which have been studied over the years, similar models, are called overstress models. The stress is over the value required to initiate yield. And if you have tau less than root 2k, that just means you have a rigid motion. Okay, d equals 0, there's no flow. So that's the essential and very important distinction between this model and a non-Newtonian fluid. It's this stipulation that tau has to satisfy this inequality in order to have flow, d not 0. Okay, let's do an example to see how the theory works in practice, something we can do by hand. Let's have a look at the so-called steady channel flow. So you have two parallel planes, let's say oriented along the x and z direction. So x horizontal and z into the plane of the screen. And you have material sandwiched in between those two parallel planes. Say they're rigid planes. And let's suppose we have a flow of that material in between, a velocity distribution, which varies with y, the x2 coordinate, so that it varies as you go from one of the parallel planes to another. Very simple kind of flow, just one unknown, v is a function of y, that we need to solve for as far as the motion is concerned. And let's have a look at what this viscoplastic theory says for this kind of flow. First thing to do is we want to compute d, which means we first need the velocity gradient. The spatial velocity gradient, L grad v, is equal to grad v. That it just is the tensor such that L dx is dv, right? The chain rule. L is the spatial gradient of v. dv, we take a derivative, so that's d of the scalar v, which is v prime y dy, times e1, which is constant along the x1 coordinate direction. So that's v prime y e1 dy, on the other hand, is e2 dot dx. And I can factor out then this dx from this tensor product. And by comparing these two sides, I immediately conclude that the spatial velocity gradient is dv dy e1 tensor product e2. Very simple motion. D then is the symmetric part of that. And of course, that the trace of that is 0, as it would have to be for our theory, because according to the flow rule, D is a scalar times the deviatoric stress, which has zero trace. So far, this flow is admissible from that point of view. We don't yet know if it satisfies equations of motion. Let's have a look at the material acceleration. V dot, the material derivative, well, that's the time derivative in the spatial description holding small x fixed vector small x fixed, plus the convective part, LV, if you remember from continuum mechanics. So here in the way we set this up, this steady flow has no time derivative when current position is held fixed. It's a function of small y only, and y is E2 dot x. You hold that fixed and there's no time derivative. LV picks up an E2 dot v, but v is in the direction of E1, so this will also be 0. So there's no inertia, there's no acceleration of the material in this steady motion. So the equation to be solved, if we neglect body force, let's say, to keep things simple, the equation to be solved is divergence Cauchy stress equals 0 in the spatial description. T, on the other hand, is deviatoric stress. We've called it tau. This is the deviatoric spherical decomposition. Tau plus a third trace T identity. A third trace T is, we'll call that minus the pressure. Right? Pressure is minus 1/3 trace T. So it's tau minus P identity. So you put that in here and you get minus gradient P from this term and then divergence tau. Okay, in the constitutive equation, I need the norm of D. The norm of D is the square root of D inner product D, and D inner product D is the trace of the square of D. So we need D squared. Here's D. If you multiply this by itself, you'll get this. And the prime means just a y derivative. Okay. So if we take the trace of that, that's the squared norm of D, we just get 2 from the trace here, and then we get a half V prime all squared. So the norm of D is 1/√2 V prime. Norm, absolute value of V prime. It's just a scalar here, not a vector. Okay. Sorry about the error on the page. And then we put that in our constitutive equation for the deviatoric stress, like so. The structure of D, it just has components along E1 and E2, E1 tensor product E2 and E2 tensor product E1. So it's going to be some scalar times this parenthesis. And you can read off what that scalar is by comparing with this, where now we know the norm of D. Okay. And we get this expression here. Norm of D, on the other hand, we've just computed in terms of V prime, put that in and you get this. So tau, this is the shear stress on the 1, 2 axes, the XY axes, will just be a conventional viscous part plus the part due to plasticity. And the lesson of this exercise is that this only is a function of y alone. And that knowledge of that fact will help us solve the equation of motion. So if you look at the expression for the stress, right, that's minus P identity plus this tau, this tensor here. So that tells you that the 1, 1, 2, 2, and 3, 3 components of the Cauchy stress are all equal to this, all the same and equal to minus the pressure. And the 1, 2, and 2, 1 components are just equal to tau. All other stress components are 0. And in the equation of motion, we need the spatial divergence of tau. In Cartesians, that's tau ij comma j ei. And let's see, you have when you do the sum here, you'll get a 1, 2, comma 2, E1, and then a 2, 1, comma 1, but T21 only depends on X2, not on X1. So this is the only term that survives. And that's very simple. You just get the derivative of tau with respect to y along E1. Then the equation of motion tells you the pressure gradient is the divergence of this tau. In general, the pressure gradient, this vector, would have components along E1 and E2 and E3 given by P comma 1, P comma 2, and P comma 3. Well, there are no E2 or E3 components, so P comma 2 and P comma 3 are both 0, which means P only depends on X. So we'll write that, we'll write p comma 1 as p sub x to stand for an x derivative. And this equation says p comma 1 e1 is tau prime y e1. So p comma 1 is tau prime y. You can integrate this with respect to x, and you get x times tau prime y plus some constant. Okay. And here we're right. Okay. Okay. Well, we need to recall that p comma 2 is 0. So take the comma 2 of this, you get x tau double prime y is 0. And so tau double prime y is 0, which means tau is a linear function of y with a constant slope, tau prime y. Let's call it minus c. And I'll take c positive so that I can get a negative pressure gradient. So p then is minus cx, put back in this equation, plus a constant. So c would be the pressure gradient. If I take it to be positive, that means I'm looking at this situation. Here are those two parallel planes I mentioned. So the planes themselves lie in the xz plane. Let's say they're separated by a distance h. So this is the xy plane is the cross section. And with c positive, that means the pressure over here at the left is greater than it is here on the right, which means you're pushing the material from left to right. Okay, here's the only equation we have to solve for the stress is this one, the simple one. Tau prime y is minus c, a constant. That means tau is a linear function of y. Let's arrange it so that it vanishes at this center line, the center plane where y equals h over 2. So when y is 0, then you'll have a positive shear stress down here. And when y is h, you'll have a negative shear stress at the top and a linear variation in between. So this is an equilibrium then stress distribution. Okay. Let's look at the let's look at the velocity field. And just to remind us of how this works in classical fluid dynamics, let's look at the pure Newtonian case where we don't have plasticity, so neglect the yield stress part of the constitutive equation. In other words, up here at the top, let's just consider tau equal to this first term. So suppose suppose k is 0, there's no yield stress. So the material flows under any shear stress, classical fluid dynamics. So let's just look at a model with tau equal to eta v prime y for the moment. That's this one. We know tau of y now, put that in here and you get, integrate this subject to, say, the no slip condition, v at y equals 0, and you get this classical parabolic profile. This is then also 0 at y equals h at the top. You could have imposed these two no slip conditions and then gotten this stress distribution automatically. So we get the classical expected parabolic profile for the velocity distribution. So the velocity is all to the left and it varies in this manner with y quadratically. Okay, let's look at the full viscoplastic model, which is quite a bit more interesting. We need to determine whether or not our flow condition is satisfied. The norm of tau has to exceed root 2 times the shear stress in shear. Otherwise, there's no flow, d equals 0, right? So we need to look at that first. The squared norm of tau is the trace of the square of tau. And if we square the tau we had a moment ago, tau tensor was tau scalar E1 tensor E2 plus E2 tensor E1. Square that and you get this expression for tau squared. Trace of that is 2 tau squared. So that's the squared norm of tau. So the norm of tau itself is root 2 times the absolute value of this scalar tau, which is in our solution is both positive and negative. depending on the value of y. To get flow, we require that this be satisfied, which means the absolute value of our shear stress has to exceed K as expected, right? Because K was the yield stress in shear, and we have a state of pure shear stress here, apart from the pressure. We've already solved the pressure, right, essentially. Okay, let's first look at the region where tau itself is positive, which is below the midplane h equal 2. For y less than h over 2, our previous solution for the stress indicates that tau is positive in that region. And in that region, absolute tau is equal to tau itself. So we have flow when tau of y that we solved is greater than or equal to the yield stress in shear. Tau of y was this linear function of y right here. Impose the inequality that this should be greater than or equal to k for y less than h over 2. And you get this restriction, that y is less than or equal to h over 2 minus k over c. Remember, c was the pressure gradient. And so actually, so you're only going to get yield then when y doesn't go all the way up to the midplane h over 2, but it only up to this value of y, which we call y bar, which is less than h over 2, because c was positive and k is positive. Okay. So of course, for this discussion to make sense, y has to be positive, right? Because the material is bounded between y equals 0 and y equals h, so y is positive in particular. And that puts a restriction on involving h and c, right? So for this to make sense, h has to be, the thickness, the distance between the plates has to exceed this, 2k over c. Or you can rearrange this as an inequality that c must satisfy. So c has to be big enough, the pressure gradient has to be big enough to initiate flow. If c is such that this inequality is not satisfied, then the system is rigid and there's no flow. Okay, so if we think along the lines of our viscous flow problem, let's say we're close to the bottom boundary where y equals 0, we expect the velocity distribution to look something like this, right? And so it's natural to assume then that the derivative of v with respect to y is positive in this regime. So let's make that assumption and then verify it later. Okay, that means that, remember, our constitutive equation involves, if you go back a page, v prime y divided by its absolute value. If v prime is positive, which we'll assume provisionally and then check later, then this ratio is just 1. And then the stress becomes just this right here. Tau is the purely viscous part plus this yield part. So we can solve this for v prime y. And we get this. Now, indeed, tau minus k, because of this restriction, is positive for y less than y bar. And so our assumption is consistent. In other words, the assumption that v prime y is positive yield is confirmed by this result here. Okay, so we can then go ahead and plug in tau of y from our previous page, and we get v prime y is equal to this. And that's valid again for y between 0 and y bar, the y bar that we've just defined up here, this y bar. We can, so including y equals 0, it's valid all the way down to the lower boundary. If we invoke our no slip condition at the lower boundary, where y equals 0, we can integrate this immediately and we just get this velocity distribution, which differs from the parabolic profile by this term here, pertaining to yield. So it's not quite a parabolic distribution. It's still quadratic, but not the same kind of parabola that we had before. And again, this is valid for y between 0 and this y bar that we just introduced. Okay. What about values of y between this y bar and the mid-plane, where y equals h over 2? Well, according to our stress field that we found, we still have tau positive in that region. In fact, it's 0 at h over 2. It's positive below h over 2, but it's less than k, right? Because that's how we derived this expression for y bar. So for y between y bar and h over 2, tau is positive, but less than the amount required to produce yield. So in particular, the absolute value is less than k, and hence the motion in that particular region is rigid, d equals 0. And for this flow, that means dv dy is 0. So v is constant in that region, and hence just equal to the value of v at y bar. This v evaluated at y bar, okay? For y above y bar, it just stays stuck at that value, and you have what we call a rigid plug in the center. So we have a flow that looks like this. Here we've arranged it so the pressure gradient is such that you have a high pressure at the left and low pressure at the right, so you're driving the material from left to right. And we have this quadratic velocity profile up to the value y bar, which is below h over 2 by the amount k over c, positive number. For y between y bar and h over 2, you just have this constant velocity. So, and by the symmetry of the problem, you can do the region above h over 2 is, by symmetry, it's just the same kind of velocity field. So the center region here just translates as a rigid body to the right. And then there's a transition to meet the no-slip condition here, given by this quadratic velocity distribution. So for obvious reasons, this is called a plug flow. And so in the viscoplastic material, because of the yield phenomenon and the threshold that's required to produce flow, we get this interesting plug flow, quite distinct from the purely viscous or Newtonian solution. And again, we have that restriction on the pressure gradient that has to be satisfied for the solution to make sense, right? And we could rearrange this as a restriction on the value of c, which was the pressure gradient. So the pressure gradient has to be sufficiently large for the solution to be meaningful. If c violates this inequality, in other words, you have this, then there's no flow at all. The material simply remains stuck in between these planes. Even if you have a pressure gradient, it just remains stuck as a rigid body, subject to the no slip condition, so it just remains stationary. And in order to get a flow to happen, then C has to meet, the pressure gradient has to meet this threshold value, and then you begin to initiate a solution like this. So it starts out as a wide plug and then gradually develops. Okay, so that gives you a feeling. I think this is the first time we solved the problem in the entire course, so it gives you a feeling of a feel for how plasticity works. And that's the so-called viscoplastic problem. By the way, there's more than one way to add viscosity to the constitutive equation for pure plasticity. The so-called Bingham plastic model is just one of those, and that's the classical model. That's the most frequently used viscous extension of plasticity. Okay. Let's go back for a while to the classical theory without the additional viscous term. The classical theory of rigid plastic solids, isotropic materials, where, again, the elastic strain is is not literally zero, but it's so small compared to the overall strain produced in a deformation that we can neglect the elastic strain, and that gives us this idealized model. This model, there's a huge literature devoted to this model, as you can imagine, because the model basically goes back, 150 years, right? So in the interim, there's been a gigantic literature that's developed surrounding specific solutions to problems based on this constitutive model right here. And we should pay homage to some of that literature in this course, because otherwise we would be overlooking some major developments in the subject. So let's spend a little time looking at this particular model. I'll mention some standard references as we move along, but in particular, this model turns out to be amenable to explicit analysis in the case of two-dimensional flow. So we could look at the theory for so-called plane strain or plane flow, two-dimensional flow, and there's a particularly well-developed theory and literature associated with that that's called plane strain slip line theory. And most of the known solutions in plasticity theory are for this special case of where we use this constitutive formulation in the context of plane deformations. So it's called plane strain. All the deformation takes place, say, in the XY plane or X1, X2 plane. So let's look at that special case and look at some of its interesting features. So let's, for the moment, talk about plane motions, that is velocity fields, that take place in the X1, X2 plane. So the Greek indices will be summed from 1 to 2, always, V alpha, E alpha. And the components, V1, V2, will suppose depend only on X1 and X2. So it's a truly two-dimensional problem. Okay. This model turns out to have some really odd mathematical properties, which will turn out, it turns out that those odd features make it relatively easy to solve problems. Okay, so along with this two-dimensional velocity field goes a two-dimensional rate of deformation tensor with components d alpha beta 1 and 2, the symmetric part of the velocity gradient, so this would be the Cartesian expression. And according to equation 1 here, a two-dimensional d will give rise to a two-dimensional deviatoric stress tau, right? So tau, the deviatoric part of the Cauchy stress, is also two-dimensional. Okay. And if we remember that the Cauchy stress is the deviatoric part minus the pressure times the identity, we can read off the stresses. Say, for example, T11 is going to be tau 11 minus P. T22 is tau 22 minus P. T33 is just, there's no 3,3 part of tau, so it's just minus P. And this gives us a way of interpreting the pressure mechanically. For example, the traction on the plane itself. So the plane is, say, the page of your computer, the plane of your computer screen. The normal to that is E3, let's say, and T on E3 is the traction on that plane. That's going to be tau E3 minus P times E3, identity on E3. Tau E3, there is no tau E3, because tau is purely two-dimensional, so you just get minus P E3. And TE3 would be T sub I3 EI. But T sub 1,3 and 2,3, T13 would be tau 13, and there is none because there's no corresponding term here. T23 would be tau 23, which is also 0. So this sum would just give you T33, which is minus P. So you can think of minus P then is the traction required to maintain the state of plane strain. It's the track, you can think of the pressure, which is a three-dimensional idea, in this context is also, apart from the sign, it's the traction required to force this two-dimensional flow situation to be maintained. Okay? So we would have to somehow supply this pressure distribution on the plane in order to maintain the two-dimensional state of flow. Okay, so the pressure is minus the third trace T, of course. So we have this. Trace T is just T11 plus T22 plus T33. T33 is already minus P. So we get T minus T alpha. This is the trace of the two by two submatrix of stress components. And so let's see, you solve this for P and you get minus a half T alpha alpha. So interestingly, the pressure is also, it's not only minus 1/3 the trace of the three-dimensional stress state, it's also minus 1/2 the trace of the two-dimensional in-plane stress state. Okay, so let's look at the yield criterion. Remember, we took some pains to justify the von Mises yield criterion. If you look back on page 109, you'll see that we expressed that in terms of the deviatoric Cauchy stress, and that's given right here. We've already used that earlier today. So we want to know what's the state of stress such that this is zero, the yield condition is satisfied, in this context of plane strain. Well, this says 2k squared is the squared norm of tau, that tau inner product itself. Tau is two-dimensional. If you work it out in Cartesians, you just get this. Tau, on the other hand, is T plus pressured identity. Do that again here, just picking up the two-dimensional components. And then just multiply terms out, you get tau alpha beta, T alpha beta, T alpha beta. Then you get delta alpha beta, T alpha beta is T alpha alpha, if you sum on beta, plus the pressure. Then you get the same thing from this cross term here, so you get two of those. And then you get P squared, delta alpha beta is same as delta alpha alpha, if you sum on beta. This is the number 2, right? It's the delta 1, 1 plus delta 2, 2. Let's see, T alpha alpha is minus 2p, with the 2p is minus 4p squared, plus 2p squared is minus 2p squared here. And then you can replace p by this expression, and then you have something that involves only the in-plane components of the stress. So this is the yield condition for the case of plane strain. And if you do the sums here, the double sum here, and do the square, you can recast that immediately in this form in terms of the explicit stress components. Okay, so that's the von Mises yield condition for plane strain. And by the way, although we're not talking about the Tresca yield function here, if you look it up and then look at what it yields in the case of plane strain, you'll get exactly the same formula. So interestingly, von Mises and Tresca coincide for plane strain. Not in other modes of deformation in general, but certainly for plane strain. Okay, well, it turns out to be useful to write the stress in terms of the principal stresses, that is the spectral form. So let's write the stress tensor in spectral form. That means we compute the eigenvalues, we'll call them T sub I, and the corresponding eigenvectors, orthonormal eigenvectors, U sub I. And you all know how to get those principal stresses. So there's the eigenvalues, the principal stresses, and these eigenvectors are the principal axes of stress. And the way you get the eigenvalues is just by writing down the matrix of stress components, which in the case of plane strain is T1, 1, 1, 2, 2, 2, 1, 2, 2, 3, 3, and there's 1, 3, and 2, 3 are 0. Subtract T, the eigenvalue, from the diagonal, expand the determinant, and you get this cubic equation where you can factor out the linear part, a linear part here. So we want the values of T that are such to satisfy this equation. One value is just given by the parenthesis equals 0. Let's call that the third root. There'll be three roots because this is a cubic equation, of course. Let's say the third root, T3, is the one that satisfies this parenthesis equals 0. So that'll be T33, which is minus P. So the third principal stress is just minus the pressure. And the other two principal stresses are the roots of the quadratic equation formed by putting the square bracket equal to 0. If you expand that out, you get T squared minus the trace of the two-dimensional T stress times T itself, the eigenvalue, and then plus determinant of the two-dimensional matrix, this 2 by 2 submatrix. And that quadratic then has these two solutions, right? This quadratic formula. And that involves this square root of this combination. And that according to the yield criterion, what's inside the curly bracket in the square root here is just 4k squared, where k is the yield stress. Take the square root of that, you get 2k, and the 2 goes with the half, and you just get k, and then you have the two roots, plus and minus. Whereas 1/2 T11 plus T2, that was a half T alpha alpha, is just minus P. So we get the two other principal stresses. Let's say T1 is the larger one and T2 is the smaller one, and T1 is minus P plus K, T2 is minus P minus K, and T3 is just minus P. So if we put those roots then back into the spectral form from the previous page with the eigenvectors, we get this. This is the identity written in terms of the eigenvectors, an orthonormal basis, where U3 is E3 because T3 is associated with 3 direction. So the third principal axis is just E3 perpendicular to the page. Then by the orthonormality, the remaining U1 and U2 lie in the plane of the screen. So we get a minus P common to U1, U2, U2, and U3, U3. So that factors out, you get the identity. And then you have a K U1 tensor product U1, and then a minus K tensor product U2, U2. So we get K U1, U1 minus U2, U2. So we rewrite that this way. So this second part, that's our deviatoric stress, because it's the part that's left over from after you subtract P times the identity. Okay, well, so that's interesting. It gives us a kind of the structure of the stress field. Of course, P and U1 and U2 can vary with position in the cross-sectional, in the x1, x2 plane. However, they're everywhere orthonormal vectors. They lie in the x1, x2 plane. We can get a little more insight by picking two other vectors. So here, say, our U1 and U2, orthogonal unit vectors at a particular point in the x1, x2 plane. Let's introduce two other vectors, T and S, that bisect the principal axes. So let's say T is, if they bisect, then they'll be at angles 45 degrees down from U1, let's say. That angle there is pi over 4. That defines the T direction. And the S direction is orthogonal to that, so it's bisecting U1 and U2, those principal axes. And let's introduce an angle theta, we'll talk about it later, which orients T with the angle between T and E1, or T and the x1 axis. Okay, so you can see immediately U1 and U2 we can decompose in this orthonormal basis consisting of T and S. And you'll just get this, because the angle here is 45 degrees. It'll be root 2 over 2 s plus t. That gives you u1. u2 is root 2 over 2 s minus t. We're going backwards along t here, hence the minus sign. And if we come back, use these expressions and form these tensor products here, we'll find that we just get tensor product t, tensor product s plus s, tensor product t. And then our stress looks like this, which gives us a nicer interpretation, because this K is a shear stress on the axes TS. And we don't know the orientation of U1 and U2, because we'd have to know the stress state completely to get those eigenvectors. And so we don't know orientation of T and S to the same degree. So this is just as useful as the previous representation. And this factor in front then must be the shear stress on those ST axes. And that shear stress we see is just K, the yield stress in shear. So somehow we have shearing along these T and S axes, right? The yield stress along these TS axes is just the yield stress itself in shear. So we expect these T and S axes to play a very significant role in the theory, and indeed they do. So we can read off immediately, this must be the deviatoric stress in plane here. S and T lie in the x1, x2 plane. Okay. We want to solve again the equilibrium equation. Let's say we're looking at a case of steady motion, let's say, where we don't have acceleration in the material. So we solve the equilibrium equation if we suppress body force, which says div t equals 0. In other words, grad p is div tau. And div tau, let's assume that we have what's called a case of perfect plasticity, where k is just a constant. In general, the yield stress k could change as you strain the material, but we could also contemplate the special case in which it's a constant. So if you look at a plot of tau versus, say, shear strain, it would just be a vertical line until you reach tau equals k, and then it would be a flat line thereafter. Okay, that would be the case of so-called perfect plasticity. This means we're suppressing a phenomenon called strain hardening of the material. We'll come back to that later. Okay, so for the time being, let's investigate this idealization in which k is a material parameter that never changes. That's called the perfectly plastic solid, for obvious reasons, non-hardening solid. And if that's the case, k is just a number, and I can take it outside the divergence, right, and put it in front here. Okay. Turns out that even though this is an idealization, it's quite a realistic one for many metals. For example, the cast iron is quite a soft material and conforms pretty closely to this idealization. Okay, so to make progress, we're going to have to take the divergence of T tensor product S and the divergence of S tensor product T. As a little aside here, let's look at the divergence of a tensor which itself is a tensor product of two vectors, say A tensor product B. In Cartesians, you would take the ij components of this tensor, namely ai, bj in this case, and take a partial derivative of the whole thing with respect to xj, and then multiply by ei and do the double sum. If you carry out this partial derivative, you have ai comma j bj, and then ai bj comma j. You recognize bj comma j as the Cartesian form of the divergence, and then ai ei gives you the vector a back again. This is the ij component of the gradient of a, that's a tensor, and then aij bj is gradient a operating on b. Okay. That's the I components of this resultant vector. So we can use that in our case. Let's take the k over to the other side and combine it with, sneak it back in the gradient of p. And using this rule, we'd have grad t operating on s plus div s with a t left over, and then grad s operating on t and a div t with s left over. Okay, so in the previous slide here, I introduced an angle theta that orients the t-axis relative to the x1 axis. Theta will vary with position in the plane, so it's a function of x1 and x2. So we define an angle theta which can be variable in the plane such that t is cosine theta e1 plus sine theta e2, s, the orthogonal vector, minus sine theta e1 plus cos theta e2 to conform to that figure. Okay, so I need stuff like gradient t and divergence of t, right? So let's see, gradient t is the tensor which operates on dx to produce dt. That's just the chain rule. Okay. And so on. I'm getting ahead of myself. So, to figure out gradient t, we need dt. dt, if you look at this formula, is minus sine theta d theta along e1 plus cosine theta d theta along e2. In other words, it's this vector times d theta. And likewise, ds, which we'll need later, is minus t d theta. So there's a sign here, not a plus here and a minus here. Okay. So let's see. Grad t dx then is dt, which is s d theta, but d theta, the chain rule, is grad theta dot dx. Grad theta is a vector. Right? So we get dt is s d theta, that's grad theta dot dx, and I can extract here a tensor product, s tensor product, the vector grad theta, all operating on dx. Compare both sides and I get grad t as s tensor product grad theta. One thing that I need from this is grad t operating on s. Now I have grad t, I can operate on s. When I do that, I pick up a dot product s dot grad theta with an s left over. And I also need a div t in the equilibrium equation. Div t is trace grad t, that's easy. That's just the trace converts this tensor product to a dot product, and I get s dot grad theta. Same procedure gives you gradient of the vector s is minus t tensor product grad theta, grad s on t minus t dot grad theta with a t left over, and div s is trace grad s minus t dot grad theta. So if I put all those now into this formula and clean it up a bit, I will get the gradient, the pressure gradient divided by my fixed constant k is 2 times s dot grad s along s minus t dot grad t along t. Bring the 2 down to the other side and we get this. That's my equilibrium equation. What are the unknowns? The unknowns are p and theta, because if you know theta, you also know t and s. Okay, so this is a vector equation. I can project it along E3, for example. Take a dot with E3. The dot with E3 dot s is 0 and E3 dot t is 0 because they lie in the plane. So we get E3 dot grad p over 2k equals 0. K is a constant. That just tells you the pressure does not depend on x3. It's only a function of the cross-sectional coordinates, x1 and x2. Okay. The remaining possibilities then are, I can project this onto E1 and E2, or since I have I have the equation nicely decomposed already along the t and s axes. I might as well project this vector equation on the t and s axes. For example, if I project on t, just dot through with t, I get t dot grad p over 2k. And I get t dot s is 0 here, t dot t is 1. So bring this to the other side, I get t dot grad theta combines with this term. And that all has to be 0. Likewise, I can take this equation and project it along s, and I get this equation here. Okay? And these equations are kind of remarkable. What they say is, well, let's see, what does t dot grad mean? It means this is the directional derivative along the curve with unit tangent t. So you can think of t and s as being tangents to certain orthogonal curves. They're curves in the plane. They're orthogonal to each other. And at every point, one curve has a tangent t and the other one has an orthogonal tangent s. This says that the derivative along the first curve with tangent t, this is a directional derivative, the derivative along that curve of this parenthesis is 0, which means this parenthesis is constant everywhere along that curve. Likewise, this equation says that the derivative along the s trajectories of this combination is 0, which means this parenthesis is constant everywhere along a curve with tangent s. And that's a very unusual mathematical structure to have. Okay? These equations go back to Prandtl and Henke almost 100 years ago. And these two equations, this one is not interesting. It just tells us P depends on x1 and x2. And that dependence is then governed by these two equations. This is a system of two equations for the two unknowns, P and theta. Remember, if we know P and we know theta, that means we know the pressure and the deviatoric stress completely, right? So that means we know the entire stress state. Knowledge of P and theta is equivalent to knowledge of the stress state. So we have two equations in these two unknowns. So in principle, we have enough equations to solve for the stress state, and we haven't said anything about the deformation or the flow, right? These equations we have not invoked any assumptions about the flow field, apart from the plane deformation. Okay? So in the vernacular, we would say that the stress state is statically determinate. You may have heard that about statical determinacy in your undergrad days. That just means you can obtain the stress field without knowledge of the deformation or the flow in principle, just by solving these two equations, assuming that you have boundary conditions that allow you to complete the solution of these two equations, like pure traction boundary conditions. So granted suitable boundary conditions, you can determine the stress without any knowledge whatsoever of the deformation or the flow. And that's, a big surprise. It's very unusual in circumstance in solid mechanics. For example, in elasticity theory, that does not happen. In order to solve for an equilibrium stress field, you have to know the deformation. In other words, the way you'd normally do it is you use the stress deformation relation from elasticity, plug it into the equilibrium equations, and you get 3 equilibrium equations for the 3 displacement components. And then after you solve the displacements, then you get the stresses. Here, it's the reverse. You can find the stresses without knowing anything about the deformation. So that's a very unusual situation. As we mentioned a moment ago, because of those two equations, those directional derivatives are 0, which means, for example, P plus 2k times theta, that's this parenthesis, just multiply through by 2k. This is constant along a trajectory with tangent t. That trajectory has, remember that t was inclined at the angle theta, so its slope is tangent theta. So on this set of curves with this satisfying this differential equation, dx2 dx1 or dy dx equals tangent theta, on that set of curves, p plus 2k is a constant. It can be a different constant along each, this is just a family of curves, right? So on a given member of that family, this will be some constant. On a different member of the same family, it will be some different constant. But the point is, this combination is constant along any one curve of this family. Likewise, this equation says that this parenthesis is constant along the curves with this tangent, which is the orthogonal trajectory to the first set of curves. So the orthogonal trajectory of this family of curves are this family of curves with this slope minus cotangent, the same theta. And then this combination is constant along each member of this family. As you go from one member of this family to another member of the same family, the constant can change, but along any particular member of that family, you get a constant. And so from these facts, you could figure out, in principle, the stress field, and we'll do examples to show that. So this is a really weird situation mathematically. It's unheard of in elasticity. It's totally different from the mathematical structure of elasticity. If you have a background in partial differential equations, you may have encountered something similar to this. This combination being constant, these two combinations, we call these Riemann invariants. The same Riemann that we know already. In the theory of partial differential equations, these combinations that are constants they're called Riemann invariants, and they're associated with a non-elliptic set of differential equations. The equilibrium equations that we've reduced to this form turn out to be of hyperbolic type. If you've encountered PDEs before, the equations of plane plastic flow are hyperbolic in character. And whereas the equations of elasticity, for example, are elliptic in character, elliptic type, a dramatically different kind of partial differential equation. And these so-called hyperbolic equations generate these so-called Riemann invariants that you do not find in elliptic systems, of which elasticity is a sort of typical example. So you could be a wonderful elastician, a great elastician, and that wouldn't help you at all in solving problems of plasticity, plane plastic flow, because the mathematical structure is so different. Vice versa, you could be really adept at solving these equations, and that experience would not help you at all in solving elasticity problems. So I think we're close to the end, so I think I'll stop here. Of course, we're not done, even if we succeed in solving these equations, as we'll do by example, to get the stress field. We want to make sure there's a corresponding velocity field, right? Because the constitutive equation relates the stress field to the rate of deformation, which involves the velocity field. So we want to make sure, let's say we get a stress field, so we know tau. We want to make sure that there exists a velocity field such that this formula is satisfied with lambda non-negative. Lambda non-negative, remember, ensures that we have dissipation in the material. So it's a physical requirement. So next time we'll consider, given these conditions, how do we get the velocity field? How do we construct a velocity field that's consistent with the stress field? Okay. So I will stop here unless there are some questions. So we'll do a number of very interesting examples once we set up this framework. Okay, so if there are no questions at this stage, then I will see you next time.